Microsoft has been able to create a quantum computer with 8 qubits, creating a quantum computer which many people thought we would never see. And now we can see it in the laboratory.
Microsoft spent nearly 2 decades and billions of dollars chasing a particle most physicists doubted even existed, building labs across continents and staking their quantum ambitions on what some called the ghost. Then suddenly, the data stopped holding, and what followed became one of the most significant, quietly handled collapses in modern physics. What this has to do with xAI's Grok lab raises even bigger questions. Do you think something major is being covered up? Yes or no? Let us know in the comments. Why computing has a ceiling? To understand what Microsoft was attempting and why the attempt mattered enough to justify 2 decades and billions of dollars, you have to understand the problem that quantum computing exists to solve and why that problem is not a technical inconvenience, but a hard limit built into the architecture of every classical computer ever made. Every device running on classical computing, every smartphone, every laptop, every server farm, every supercomputer, processes information using bits. A bit is a switch that is either off or on, 0 or 1. The entire edifice of modern computing, everything from weather forecasting to financial modeling to the algorithm determining what appears on your screen right now, is built from combinations of those two states arranged in sequences of extraordinary complexity. The achievement represented by what classical computing has produced in under a century of development is genuinely remarkable. But the architecture has a ceiling, and the ceiling is becoming relevant. There are classes of problems that classical computing cannot solve in any practical time frame, regardless of how much processing power is applied to them. The interactions between molecules in a drug candidate and the proteins in the human body involve quantum effects that classical computation can only approximate, not model accurately. The atmospheric system's driving climate involves so many interacting variables at so many scales simultaneously that the models classical computers can run are necessarily simplified to the point of losing significant accuracy. The folding behavior of proteins, which determines their function and whose misfolding underlies diseases including Alzheimer's and many cancers, involves quantum mechanical effects that classical simulation cannot capture faithfully. These are not obscure academic problems. They are the specific problems whose solution would produce transformative medical, environmental, and industrial capabilities. They are also the problems that classical computing, regardless of how much faster processors become, cannot solve because the fundamental architecture of classical bits is the wrong tool for the job. Quantum computing was developed as the right tool for exactly this class of problem, and Microsoft's 2-decade pursuit was an attempt to build that tool in a form stable enough to be useful. How quantum computers work. A quantum computer replaces classical bits with qubits, quantum bits that exploit properties of quantum mechanics that classical bits cannot access. The first of those properties is superposition, the ability of a quantum system to exist in multiple states simultaneously rather than being fixed in a single state until measured. A classical bit is always either 0 or 1. A qubit in superposition is effectively both simultaneously, collapsing to a definite state only when measured. The second property is entanglement, the quantum mechanical correlation between particles that allows the state of one to be instantly correlated with the state of another, regardless of the physical distance between them. When qubits are entangled, operations on one immediately affect the correlated state of the other, allowing quantum computers to process information in a way that scales exponentially rather than linearly with the number of qubits involved. The numbers that result from that exponential scaling are difficult to hold in the imagination. 10 qubits in superposition can represent more than 1,000 states simultaneously, giving a quantum computer with 10 qubits of processing capacity roughly equivalent to a classical computer with 1,000 bits. 50 stable qubits can rival the most powerful classical supercomputers. 300 stable qubits operating without error can represent more states simultaneously than there are atoms in the observable universe. The theoretical power of a working quantum computer is not a modest improvement over classical computing. It is a different category of tool entirely. The operative word in all of that is stable. Qubits are extraordinarily fragile. They are destroyed by stray photons, by the slightest vibration, by the thermal noise produced by ambient temperature. The quantum state that gives a qubit its computational power is called coherence, and it is lost almost instantly when the qubit interacts with anything in its environment. This problem, called decoherence, is the central engineering challenge of quantum computing, and the reason that the theoretical power of quantum systems has proven so difficult to realize in practice. The companies pursuing quantum computing have addressed decoherence through quantum error correction, using dozens or hundreds of physical qubits to encode a single logical qubit that is protected against the errors individual physical qubits inevitably produce. Google and IBM have pursued this approach using superconducting circuits operating at temperatures colder than outer space, around 15 millikelvin, which is colder than the average temperature of interstellar space. The approach works in a limited sense. It produces quantum computers that can perform specific operations. It also requires enormous overhead in physical qubits per logical qubit, limiting how many logical qubits any practical system can maintain. Microsoft looked at this approach and made a decision that stunned the physics community. They rejected it entirely and chose to pursue a theoretical particle that had never been observed and that most physicists were not certain existed. The ghost particle. Ettore Majorana was an Italian physicist who published a paper in 1937 predicting the existence of a class of particle with a property unlike any particle previously described. A Majorana fermion would be its own antiparticle simultaneously, existing in a state between matter and antimatter that standard particle physics did not accommodate. The prediction was mathematically elegant and physically bizarre, and it sat for decades as a theoretical curiosity with no experimental evidence to support it. Majorana himself disappeared the following year, in 1938, vanishing from a ferry between Palermo and Naples without explanation or trace. The mystery of his disappearance has never been resolved. The particle bearing his name remained, for most of the following half-century, a mathematical object with no physical reality, established by any experiment. In the early 2000s, theoretical physicists developed a proposal for how Majorana fermions might be engineered into existence in a laboratory setting, using semiconductor nanowires placed in proximity to superconducting materials under specific conditions of magnetic field and temperature. At the ends of these engineered nanowires, theory predicted, Majorana fermions would appear as quasi-particles, not fundamental particles in the particle physics sense, but collective excitations of the material that exhibited Majorana-like properties. These engineered Majorana quasi-particles would be theoretically useful for quantum computing in a specific and transformative way. The property that made Majorana fermions valuable to Microsoft's quantum ambitions was their predicted resistance to decoherence. In a topological qubit built from Majorana fermions at the ends of a nanowire, the quantum information would be stored not in the state of any individual particle, but in a global property of the system, specifically in the topological relationship between the Majorana fermions at each end of the wire. This property, described by researchers as analogous to a knot tied in the fabric of space, is protected by the mathematics of topology itself. You cannot destroy a knot by making small local perturbations to the material around it. You have to undo the entire knot, which requires a global disruption of the system rather than the local noise that destroys conventional qubits. If topological qubits worked as theory predicted, they would be inherently stable without the enormous error correction overhead that conventional approaches required. A quantum computer built from topological qubits would leapfrog every competitor not through incremental improvement, but through a fundamental architectural advantage. Microsoft would go from having no working quantum hardware to having the best quantum hardware in the world overnight. The risk was that before any of this could be built, someone first had to prove that Majorana fermions existed in engineered materials. Nobody had done that. The entire strategic bet rested on a particle that existed. At the time, Microsoft made the decision to pursue it, only in the mathematics. The rise. Microsoft's quantum program assembled a research team that represented a genuine concentration of the relevant expertise available in the global physics community. Leo Kouwenhoven, one of the world's leading experimental physicists in semiconductor nanowire research, was recruited from Delft University of Technology in the Netherlands, where his group had been doing some of the most advanced work on the kind of systems that the Majorana proposals required. Research facilities were established at Delft, in Sydney, and at Microsoft's own campuses, creating an operation that spanned 3 continents and involved hundreds of researchers working on the interconnected problems of nanowire fabrication, superconducting interfaces, measurement protocols, and the theoretical framework for interpreting the data. The engineering challenges were extraordinary even before getting to the physics. The nanowires at the center of the Majorana proposals had to be fabricated with atomic-scale precision, their interfaces with superconducting materials controlled at a level of quality that required new fabrication techniques to be developed specifically for the project. The measurement systems required to detect the signals predicted by theory had to operate at temperatures close to absolute zero, while achieving sensitivity levels at the boundary of what measurement technology could achieve. In 2018, the program produced what appeared to be the breakthrough it had been building toward. A paper published in Nature, one of the most prestigious scientific journals in the world, reported the observation of a quantized conductance plateau in the nanowire systems being studied, a specific electrical signature that theory predicted would appear in the presence of Majorana fermions. The paper was authored by Kouwenhoven's group and co-authored by Microsoft researchers. It was greeted by the physics community and the technology press as a potential smoking gun for the existence of the particle the program had been hunting for over a decade. Microsoft's funding surged. The timeline for achieving a working topological qubit was compressed from decades to years in internal planning documents. The ghost had apparently been found. It had not been found. The crack. The problem that emerged in the months and years following the 2018 Nature paper was not dramatic or sudden. It was the slow accumulation of a specific kind of evidence, the failure of other laboratories to reproduce the results. Independent research groups attempting to replicate the conductance plateau observations using their own nanowire systems and measurement setups produced inconsistent results. The signal that had appeared so clearly in the original measurements was not appearing reliably in independent attempts to observe it. Questions about the interpretation of the data began to circulate in the physics community, initially in the careful language of scientific correspondence and conference discussions, and then with increasing directness. Alternative explanations for the observed conductance signatures were identified and formalized. Andreev bound states, quantum states that can form at superconductor interfaces without any Majorana physics being involved, were shown to be capable of producing signals similar to those reported in the 2018 paper under certain conditions of disorder in the nanowire material. Dr. Fatima Shaheen, working in condensed matter physics at MIT, later described the atmosphere in the field during this period in terms that captured both the scientific and human dimensions of what was happening. Everyone wanted it to be true, she said. The particle was beautiful in the mathematics. The technology it promised was transformative in a way that none of the competing approaches could match. The desire for the result to be real was genuine and understandable, and it was precisely that desire that made the data's failure to hold up so difficult to confront directly. Science does not accommodate desire. It accommodates only what the data, rigorously analyzed, actually shows. An internal review of the 2018 data was triggered, partly by concerns raised within Microsoft's own research team. What that review found was uncomfortable. The data had not been analyzed with sufficient rigor. Measurements that did not fit the expected signature had been selectively excluded from the analysis in a way that overstated the evidence for the claimed observation. The full dataset, analyzed without the selective exclusion, did not support the conclusion the paper had reported. In 2021, the Nature paper was retracted. It was one of the most high-profile retractions in the recent history of physics, involving one of the world's largest technology companies, one of the field's leading experimental physicists, and a result that had been celebrated globally as a potential milestone in the development of quantum computing. Kouwenhoven stepped down from his leadership position in the program. Senior researchers departed. Internal communications that became available after the retraction revealed that red flags about the data analysis had been raised by researchers within the program years before the retraction, and that those concerns had not been elevated to the level of response they warranted. The program's central promise had cracked down the middle. The quiet shutdown. The retraction received substantial coverage. What followed received considerably less, which is one of the reasons its significance has been underappreciated relative to what actually happened. The experimental operations at the core of the Majorana program were scaled down substantially in the period following the retraction. Equipment that had been operational across the program's multi-continental facilities was mothballed or transferred. Research contracts were not renewed. Early career scientists who had built their professional trajectories around the program found themselves without positions, the most vulnerable members of a very large and expensive operation that was methodically reducing its scale without formally announcing that it was doing so. Microsoft maintained its public commitment to quantum computing and to the topological approach throughout this period, and the division was never formally dissolved. The public statements continued to describe an active and ambitious program. The reality, described by researchers who had been inside the operation, was an organization processing the aftermath of a fundamental setback while maintaining a public posture of continuity. Dr. Anil Kapoor, a former postdoctoral researcher in the program, described the experience in terms that have been quoted repeatedly in coverage of the aftermath. One month, we were building the future. The next, we were packing instruments into crates. The sensitive equipment that had been at the center of the program's experimental work was transferred or placed in storage. Nearly 2 decades of work was effectively paused, the physical apparatus of the effort dismantled across facilities that had been built specifically to house it. The quiet nature of the shutdown, the absence of a formal announcement, the maintenance of public statements that did not reflect the operational reality, is itself significant as a data point about how institutions manage the gap between scientific failure and public communication when the stakes are high enough and the investment is large enough that straightforwardness feels institutionally costly. The pressure beneath the science. Microsoft's Majorana program did not collapse in a vacuum. It collapsed in a context that explains, without excusing, the pressures that produced the selective data analysis that led to the retraction. Governments around the world have been pouring billions of dollars into quantum computing research and development, not primarily because of the medical and scientific applications that make quantum computing valuable to researchers, but because of the security implications. A sufficiently powerful quantum computer could break the encryption systems that currently protect military communications, financial transactions, critical infrastructure, and essentially every secure digital communication that exists. A nation that achieved a working quantum computer before its competitors would have the ability to read encrypted communications that its adversaries believed were secure, a strategic advantage with no historical precedent in the modern era. In that context, the pressure on research programs to demonstrate progress is not simply the ordinary competitive pressure of scientific funding. It is pressure with national security implications attached to it, pressure from government funders who are measuring investment against the possibility that a competing nation's program might achieve a working system first. That pressure does not change what the data shows. It does change the incentive structure that surrounds how data is interpreted and communicated, and it creates conditions in which the line between genuine discovery and wishful interpretation becomes dangerous to cross but easier to approach than it would be in a lower-stakes environment. Microsoft was not alone in navigating this pressure in ways that produced claims that subsequently required revision. Google's 2019 announcement of quantum supremacy, the claim that its Sycamore processor had performed a calculation that would take the best classical computers 10,000 years, was met within weeks by IBM researchers who argued that the same calculation could be performed by a classical computer in days using better algorithms than Google had assumed in its comparison. The claim was not retracted, but was significantly qualified in subsequent discussion. Across the industry, approximately $35 billion has been invested in quantum computing since 2015. Many of the quantum computers that have been built during that period cannot outperform a conventional laptop on real-world computational tasks. The gap between the theoretical promise of quantum computing and the practical reality of what current systems can actually do remains vast, and the pressure to close that gap in public communication has not always waited for the underlying science to close it first. The comeback attempt. In early 2025, Microsoft announced what it described as the world's first topological qubit processor, a chip it named Majorana 1. The announcement represented Microsoft's return to public claims about progress in the area where the 2021 retraction had most damaged its credibility, and it was made with considerably more methodological detail than the 2018 paper had provided, including multiple layers of verification and more rigorous protocols for distinguishing genuine Majorana signatures from the alternative explanations that had undermined the earlier work. The reactions from the physics community reflected the history that preceded the announcement. Researchers who had followed the program's trajectory closely were split between genuine cautious optimism about the methodological improvements and pointed skepticism about the significance of any new claim from a program with the Majorana program's track record of premature announcement. Dr. Priya Natarajan, a physicist whose work on quantum systems had made her a respected voice in assessments of quantum computing claims, responded to the Majorana 1 announcement with a phrase that captured the skeptical position precisely. "We have been here before," she said. "The history of Majorana fermion research is littered with premature announcements. Belief is not evidence. Independent replication is evidence. And as of the time of writing, independent replication of the Majorana 1 results by unaffiliated research groups has not been published. The chip remains proprietary. The detailed data supporting the claims in the announcement has not been fully available to the broader physics community for independent analysis." The question that the Majorana 1 announcement raises, and that the history of the entire program makes it difficult to answer cleanly, is the question of how you distinguish genuine persistence toward a real discovery from the continuation of a search that has already produced its most honest result. At the frontier of physics, where the signals being measured are at the limit of what measurement technology can resolve, and where the theoretical framework for interpreting those signals is itself not fully settled, the distinction between a real signal and a sophisticated artifact of the measurement process can take years of independent work to establish. That uncertainty is not a flaw in the scientific process. It is the scientific process operating at its actual frontier. The larger lesson. The story of Microsoft's Majorana program is not primarily one of corporate failure or scientific misconduct, though elements of both appear. It is, more fundamentally, a story about what happens at the boundary between the known and the unknown when the stakes are high enough to distort the normal processes by which science corrects itself. Quantum computing belongs to a class of technologies, alongside nuclear fusion and artificial general intelligence, whose theoretical foundations are sound and whose potential impact is transformative, yet whose practical realization has proven far more difficult than anticipated. The physics behind topological qubits is not in doubt. What remains uncertain is whether those principles can be engineered into stable, usable systems. The obstacles are layered, subtle, and time-consuming, often extending far beyond the timelines envisioned by the teams working closest to the problem. Part of the challenge lies in the deeply counterintuitive nature of quantum mechanics. Concepts like superposition and entanglement defy everyday experience, and the same properties that give qubits their power also make them fragile and difficult to control. History shows that even successful quantum technologies, such as lasers, semiconductors, and MRI systems, required decades to evolve from theory to reliable application. Fully fault-tolerant quantum computing, capable of solving complex problems in chemistry, materials science, and climate modeling, remains distant. Most careful estimates place it at least a decade away, and possibly several. The central lesson is not that the effort was misguided or that Majorana particles are illusory. It is that progress at the frontier of physics is inherently nonlinear and uncertain. Paths that appear promising may lead nowhere, and those that succeed often do so unpredictably. Researchers who questioned the data were justified, and those who believed in it were not acting in bad faith. They were navigating ambiguity under pressure, where the line between hope and evidence can become difficult to see clearly. What the signal means. Somewhere in a laboratory right now, a physicist is looking at a signal on a measurement system that could be the thing the field has been looking for, or could be an artifact of the measurement process. The signal looks the right shape. The conditions look right. The data is within the range of what theory predicts. And the physicist is doing the thing that the history of the Majorana program most forcefully argues for: waiting. Running more measurements, bringing in colleagues to look at the data independently. Resisting the pressure to announce, because the difference between announcing a discovery and announcing a result that will subsequently require retraction is not always visible in the signal itself. It is visible only through the process of independent verification that takes the time it takes and produces the result it produces, regardless of what anyone involved in the original measurement hoped to find. The particle Majorana predicted in 1937 may still be there, waiting in the mathematics of engineered nanowire systems to be coaxed into observable existence by the right combination of material quality and measurement precision. Or the quasi-particle signatures that theorists predicted may be more difficult to distinguish from mimics than the early theoretical work suggested, and the program may eventually conclude that the approach does not yield what it promised. Both outcomes are scientifically legitimate. Both outcomes advance understanding. The first produces a transformative technology. The second produces knowledge about why a promising approach does not work, which is the kind of knowledge that eventually points toward the approach that does. Microsoft's labs are scaled back. The equipment is in storage. The researchers who built their careers around the program have moved on to other positions. The question that the program chased is still embedded in the physics, still waiting for an answer, still representing the same transformative potential that it represented when Microsoft made the decision to pursue it with everything it had. Failure is not the opposite of discovery. It is the price of it, and the laboratories that never fail are the ones that never reach far enough to find anything genuinely new. 2 decades, multiple continents, a theoretical particle that most physicists doubted existed, a landmark paper retracted, labs scaled back and equipment packed into crates, a comeback announcement still awaiting independent replication. The ghost is still out there, in the mathematics, in the engineered nanowires, in the measurements that ambiguous signals keep producing. The search was not wasted. The question is still open. Subscribe so you never miss what comes next.